long before hybrids became a big thing these days, we in chemistry had our own hybrids, hybrid orbitals or hybridization. And so we got there first. And it's one of those topics that is often presented in Gen Chem. And it's one of those things that students dutifully memorize in their big lists of things to memorize. Tables like this are pretty common. So it's not a topic that is, very difficult. It's one of those topics, though, that leaves most students going, what is up with that stuff? I mean, where in the hell did it come from? And that's actually a very good question. And so I wanted to run through like a quick example problem. This is the type of problem that comes up fairly often. What is the hybridization on the carbon bonds in these molecules, or the carbon atoms in these molecules? What is number of sigma bonds, number of pi bonds? That's all pretty, easy to do once you memorize the rules and definitions. But I wanted to talk a little bit about where did it come from? What kind of thinking went on here? Because it's actually a pretty significant and deep problem. And so I'm going to begin that, kind of explaining some of the origins of these ideas by going through a few really basic, Lewis structures for some really simple molecules, some electron configuration diagrams for the central atoms in these molecules, and then kind of see where the notion of hybridization actually came from. And I'm going to start with one of everybody's favorite atoms, good old fluorine, okay? Sits up there at the top of column 7 of the periodic table. Column 7, so we would go, little dot structures, because everybody loves drawing dots, let's face it. We would go 1, 2, 3, 4, 5, 6, 7, 7 dots, one lone pair, and we would say, oh gosh, if I were asked to draw the Lewis structure of hydrogen fluoride, it would look like this. And here I would say, oh, look, there's my fluorine with its 8 valence electrons and filled shells and all that good stuff. Same story for the hydrogens, needing only 2. 1 unpaired electron, 1 bond formed. Sure enough, we would look at the electron configuration diagram for this thing, and we'd have, 1, 2 here, and go 1, 2, 3, 4, 5, 6, 7. Oh, look, 1 unpaired electron, 1 dot, 1 bond. Everything is just great. We like that one very much. I'm going to sit and just look at it for a moment. But moving on, then we would look, because we're chemists, we want to, not just use one example. We would look at an oxygen atom. The beast up there at the top of column 6. Ooh, column 6. 1, 2, 3, 4, 5, 6. Ooh, 2 unpaired electrons. I know, let's draw a Lewis structure. And we would go here, and we'd put a hydrogen there, and a hydrogen here, and doink, 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 doink. And we would go, oh, look, 8 valence electrons around the oxygen, and 2 around the hydrogens. And we'd probably want to work and make those hydrogens a little prettier. But, And so we go, oh, look, water molecule, and we'd go 1s, 2s, 2p, and we go 1, 2, 1, 2, 1, 1, 2, 3, 4, 5, 6. 2 unpaired electrons, 2 dots, 2 bonds. Boy, 1 dot, 1 bond, 2 dots, 2 bonds. Things are looking good. Of course, being chemists, we want to expand that out a little bit, so we go to nitrogen, the element at the top of column 5. 1, 2, 3, 4, 5. Ooh, 3 dots. And sure enough, the Lewis structure of NH3 looks like that. It forms 3 bonds. We'd go 1s, 2s, 2p. We'd go here for those 2, and then we go 1, 2, 3, 4, 5. 3 unpaired electrons, 3 dots, 3 bonds. Everything is just humming along. We ought to just stop right there. We have our pattern. Things are going well. But we're going to do one more. We're going to look at carbon. Column 4 of the periodic table. 1, 2, 3, 4 dots. Oh, 4 dots, yes. We would draw a Lewis structure of a carbon-containing molecule like this one. We go 4 dots, 4 bonds, magic electron configurations, octets, all that fun stuff. Everything is humming along great. 1s, 2s, 2p, 1, 2, and got those things in. 1, 2, 3, 4. And we would go 2 unpaired electrons. 4 dots, 4 bonds, 2 unpaired electrons. 1 unpaired electron, one dot, one lone dot, one bond, two unpaired electrons, two unshared dots, two bonds, three unpaired electrons, three dots, three bonds, two dots, four unpaired electrons, four bonds. That's the problem. When you take this simple little relationship here, starting with fluorine and working your way across from right to left on the periodic table, it all makes a lot of sense until you get to carbon. And so your choices are to say, screw that and look at these, or realize this is telling us there's something a little bit more than just simplistic little dots and stuff going on here. There's something more to carbon. And it sets up a bit of a contradiction. These electron configuration diagrams here match the number of dots, match the number of bonds perfectly. This one does not. This is the electron configuration diagram, the ground state of carbon. And to be honest, there's a lot of experimental evidence for this. There are carbon atoms in the gas phase, not bonded with anything, not ions, just plain carbon atoms, do have two unpaired electrons. This is not an inaccurate picture. This reflects our understanding of carbon atoms. This reflects our understanding of how carbon forms bonds. And for carbon, these pictures and that picture don't match, whereas they do match for all of the others. And so either it's an anomaly or there's something else going on. And there is something else going on, and this observation of something that is a mismatch between the electron configuration picture and the Lewis dot picture and the Lewis structures, this mismatch between the two is what leads to the ideas of hybridization. So what I'm going to do is I'm going to remove our nice pretty ones here because they all follow the, all are pretty standard. Leave this one and we're going to kind of explore this one a little bit more. So the magic eraser, and we'll be right back. And so trying to explain this mismatch between the electron configuration diagram and the Lewis dot structures leads to the concept we now call hybridization. The one name most associated with this is Linus Pauling, one of the towering figures of chemistry of the 20th century. And his work follows on a lot of the discoveries in quantum mechanics, and it's actually a remarkably clever, pretty simple in its outline idea, okay? And so what he does is he looks at this issue, but he realizes that mathematically in the world of quantum mechanics, s orbitals, 1s and 2s, and p orbitals, and even d orbitals, they're all described mathematically as we call them wave functions. I'm not going to go into the details of that here. But he realizes that you can write wave functions for a p orbital or an s orbital, but you could also write wave functions for combinations of these things. You can literally add the two wave functions together and create a new wave function, a linear combination of the simpler ones. And he looks at this electron configuration diagram and says, if I were to take that 1 2s orbital wave function and add it to the three separate px, py, pz, the three separate p orbitals of the second principal energy level, I could create a new region in space, 4 of them, okay, 4 of them, that would combine characteristics of both the s orbital, and its pretty spherical shape, and the p orbital, and that classic dumbbell shape. He called these hybrid orbitals, and it's this that produces what most students memorize as the sp3 hybrid. This is the one that has the tetrahedral geometry, and it's simply a way of adding the electron or the wave functions, the descriptions, the mathematical descriptions of these orbitals together to create new combinations. And so he takes his electron configuration diagram for the carbon atom, which does have this configuration. It says before carbon is ready to bond, you do this. 1s, that's left alone. 2s and the 3 2p orbitals are added together. 1, 2, 3, 4 to form 4 sp3 hybrid orbitals. 1, 2, 3, 4 electrons in the second principal energy level. 1, 2, 3, 4 electrons in the second principal energy level. I'll even put the little 2 out front. 2 sp3, the sp3 hybrid orbitals of the second principal energy level. This gives us an electron configuration diagram with 1, 2, 3, 4 unshared electrons matching the 4 dots of the Lewis structure for the atom, matching the 4 bonds that carbon is known to form in its molecules. This is how Pauling explained this supposed anomaly by saying for carbon atoms and others on the periodic table, before they are ready to bond, you must hybridize them. Hybridize their valence orbitals, okay? Okay. The 1s orbitals, they're core electrons. Who cares about them? They're not on the outside of the atom, but it's the second principal energy level here for carbon. That's the one where the hybridization occurs. And so this is what leads you to say the carbon in a molecule like this is sp3 hybridized. And that's going to be true, that little rule you learn, for every carbon that has 4 single bonds on it. Okay? So I'm going to then draw another Lewis structure over here. We're going to expand this out just a little bit more and hopefully give you kind of a feel for the origin of sp3 and some of the other hybridization schemes. And so we're going to extend this just a little bit, and I'm going to look at a molecule like this one. This is carbon in formaldehyde. This is its Lewis structure. If you were asked to draw the Lewis structure of H2CO, you would come up with this. You would declare it to have a trigonal planar geometry, and you would see 3 bonds, a double bond and 2 single bonds on the carbon. Okay? This having a different geometry, it's not in the tetrahedral family of geometries the way methane is. And remember, the tetrahedral family means the tetrahedrons, the trigonal pyramids, the bent shapes like water. And in fact, all those molecules I had up there, CH4, NH3, H2O, HF, are all members of the tetrahedral family. They all have 4 sets of electrons on the central atom. This one has 3 sets of electrons on the central atom, so it has a different geometry, trigonal planar. And the hybridization scheme for something like this is a little bit different. Okay? What is done here is you say we are going to form 3 bonding regions, not 4. So we take our carbon electron configuration diagram, we're going to modify it, but we modify it this way. We take the 2s and 2 of the p orbitals. Not all 3, 2 of the p orbitals, and create the sp2 hybrid. Okay? We have 3 bonding regions around the carbon, so we create 3, there we go, 3 hybrid orbitals to sp3 hybrid, I don't know what that is, to explain that. So I'm going to apply the magic eraser here just a moment, and we'll draw that diagram. So we have to modify the electron configuration diagram of the plain old carbon atom to reflect 3 bonding regions. We do it this way, classic 1s orbitals, who cares about them? We now go the second principal energy level, sp2, 1, 2, 3, and we have to leave behind 1 of the 3 p orbitals, okay? And so we still have 1, 2, 3, 4 second principal energy level orbitals. Not all of them have been hybridized this time. Now only 3 of the 4, 1 has been left alone. We still have the 1, 2, 3, 4 electrons of the second principal energy level. 1, 2, 3, 4. Notice how that was done. We are ready to set up our 4 bonds, but you will notice very clearly 3 of these bonds are going to be different. They come from the hybrid. One of these bonds is going to be different from the other 3. It comes from the unadulterated, unmodified, unhybridized p orbital. Okay? This is what is going to be called the pi bond. This is what is going to be called the set of sigma bonds. And you learn that pretty readily. Single bonds are always sigma bonds. Double bonds are a sigma and a pi. Triple bonds, a sigma and 2 pi, 2 unused p orbitals. And so it's easy enough to memorize the rules. Hopefully you get a little bit of a feel for where some of that is actually coming from now. Okay? So I'm going to leave it there, and then we're going to put up the example question and run through that real quick. So let me apply the magic eraser, and we'll be right back. There. Now, the example problem from one of the example problems from the text is this molecule, and they ask you to determine the hybridization of the 2 carbon atoms, determine the number of sigma bonds, the number of pi bonds, and also do the bond angles. So some of that, it's all of those types of questions really are memorization questions, admittedly. This type of table, like I showed previously, this one is common in almost all the different textbooks, and yeah, it just really makes a lot of sense if you just know that information. 2 sets of electrons is linear, 3 sets is trigonoplanar, 4 sets is in the tetrahedral family, and so forth. 2 sets is sp hybridized, 3 sets is sp2 hybridized, 4 sets tetrahedral family, sp3 hybridized, and so on. Okay? Just kind of know that information so you can do a problem like this one pretty quickly. So you learn the geometry parts. We look at this carbon, we go 1, 2, 3, 4 sets of electrons on it. We know its geometry is going to be tetrahedral. There's no doubt about that. Tetrahedrons are always associated with a 109.5 degree bond angle. Slight modifications depending on size of atoms, but the basic bond angle, 109.5 degrees. So that's that one. This carbon, 2 sets of electrons, 2 bonding regions around it. That means it's going to be linear. Okay, and it's linear is the geometry, 180 degree bond angle. The new part, what is the hybridization of these 2 carbons? Okay, that follows from the geometries, frankly. Tetrahedral family, the hybridization is always sp3. Pretty 3. Okay, 4 bonds, 1, 2, 3, 4 bonds on it, sp3 hybridized. This one here, the linear family, is always sp hybridized. 1 s, 1 p orbital, the other 2 p orbitals left alone. And then sigma bond, pi bond, classic type of question. They're always going to ask it on standardized exams. One of those annoying little things to memorize. So what you memorize is this: a single bond is always a sigma bond, always, for our purposes. A double bond is always a sigma and a pi bond. Okay, the pi bond is the unused p orbital. The sigma is the hybrid orbitals. The triple bond, twinky, is a sigma and 2 pi bonds. The 2 unused p orbitals, the 1 set of hybrids. Okay, and so just have that tucked away up here. You look at this one, single. These are 4 sigma bonds here around that carbon. This carbon has, the single bond we've already counted here, but over here it has a triple bond, sigma and 2 pi bonds. The way this question is often asked, in this molecule, how many sigma bonds, how many pi bonds do you have? And for this particular molecule, you have 5 sigma bonds, you have 2 pi bonds. Okay, 1, 2, 3, 4, 5 sigma, 2 pi's. Okay. And so, like I say, answering these types of questions that will pop up on all kinds of different exams and standardized exams and all that, that's not that difficult. You've already memorized the geometries and the bond angles. Tack on sp3, sp, sp2 for the trigonal planars, and then, of course, sp3d for the trigonal bipyramid family, sp3d2 for the octahedral family. That's easy enough to do. Remember this little relationship for number of sigma, number of pi bonds, that's pretty easy to do. But the deeper question, where in the hell did all that come from? It came from this versus that, and coming up with a rather clever way to try to reconcile these pictures and expand our understanding of how these atoms, carbons and all the others, form bonds and make up the molecules that make up everything else. And so I hope that either clarifies a couple of things or deepens your understanding of how this stuff works just a little bit. And so keep it in mind, do a few more of these, and we'll talk to you later.